We focused on structural mechanics in the previous tutorials. This time we're going to perform a heat transfer analysis so you get an idea of how this is done in Abaqus. The setup consists of a copper block with its two ends held at fixed temperatures of 400 degrees Celsius and 350 degrees Celsius. One half of the top surface is exposed to a heat flux of 5,000 watts per meter squared, which will raise the temperature of the block. The other half of the top surface is exposed to air at 200 degrees Celsius, where it loses heat by natural convection. We will assume that the convection coefficient is 13 watts per meter squared per degree Celsius. We will assume there is no heat loss by radiation from this surface. One half of the left side of the block is in a vacuum and inside of another cooler body at 320 degrees Celsius. Heat transfer occurs between the two bodies only by radiation. The copper is assumed to have an oxide layer and therefore has an emissivity of 0.78. All the other surfaces of the block are insulated, meaning that no heat flows across these surfaces. You're probably thinking to yourself, this is a really strange setup, but it allows us to demonstrate how to add conduction, convection, and radiation heat transfer to your model without any other distractions. The dimensions of the block are displayed in the figure. The SI system of units is used where length is in meters. The temperature scale being used is the Celsius scale. The block is made of copper with a thermal conductivity of 401 watts per meter per degree Celsius. There are two types of heat transfer analysis, steady state and transient. In steady state conditions, the temperature differences and heat fluxes driving the heat transfer remain constant with time, and a state of equilibrium is reached where the spatial distribution of temperature does not change with time. A transient state, on the other hand, is characterized by variations in body temperature with time. In this example, we are going to perform a steady state analysis, which means that the heat transfer process has been taking place for a while, and an equilibrium state has been reached. So open up Abaqus and let's begin. Open a new file in Abaqus. Rename the default model Heat Transfer. Create a new part called Block, which is a 3D deformable solid extrusion, and set the approximate size to 5. Sketch the profile using the Create Lines Rectangle tool. Dimension it using the Add Dimension tool. Give the extrusion a depth of 6 meters. Let's create a material. In a steady-state heat transfer analysis, the only material property required by Abaqus is the thermal conductivity. We will use the material copper. Set the thermal conductivity to 401 watts per meter per degree Celsius, which is in the appropriate units since we are using SI with length in meters, and we will specify our temperatures in degrees Celsius. Moving on to sections, let's create one named block section, which is of type solid homogeneous. Ensure that the material is set to copper. Now assign the section to the part. Create a dependent instance of the part in the assembly. Now we shall partition the block. Partitions, as you know, can be created on a part or on an instance of a part in the assembly. In this case, the part has been instanced into the assembly as a dependent part instance. You may already be aware from earlier tutorials that a dependent part instance cannot be meshed in the assembly module. It is the part that must be meshed in the part module. Similarly, you cannot create a partition on a dependent part instance in the assembly module. You need to partition the part in the part module. If you try to use any of the partition cell tools in the assembly module, Abaqus will give you an error. So the first step to creating the partition is to switch to the part module using the module drop-down list. We shall create the partition by creating a datum plane where we would like the partition to be, and then use this datum plane to partition the block. Let's use the Create Datum Plane midway between 2 points tool. Abaqus prompts you to select the first and then the second point to create the partition. You might need to rotate the view in order to select the second point. Abaqus will generate the partition midway between the 2 points we selected. Now let's use the partition cell Use Datum Plane tool. Abaqus prompts you to select the datum plane. Then click the Create Partition button. You see in the viewport that the part has been partitioned. We need to create a step for the heat transfer analysis. Let's name it Heating Step. The procedure is a general heat transfer. In the Basic tab, we see two options for response, steady state and transient. Transient is selected by default, but we wish to perform a steady state analysis, hence choose steady state. Abaqus informs you that the default load variation with time has been changed to ramp linearly over the step. This means that any load you apply will have a ramp amplitude, meaning that it will increase linearly over the duration of the step until it reaches its final value. If you were to click on transient to switch back, Abaqus would inform you that the default load variation with time has been changed to instantaneous. Any load you apply will have a step amplitude, meaning that it will reach its final value instantaneously at the beginning of the step. So, to summarize, steady-state heat transfer procedures in Abaqus have a ramped load variation by default, whereas transient heat transfer procedures have instantaneous loads by default. This behavior can be changed. If you switch to the tab labeled Other, you see a section called Default Load Variation with Time with two options, Instantaneous and Ramp Linearly over Step. The user has the option of choosing one over the other right here. So if you select Steady State Response in the Basic tab, and Abaqus changes the default load variation to Ramp, you can open up the Options tab and change it back to Instantaneous. We will now apply boundary conditions to fix the temperature at two surfaces. Name the first boundary condition Constant Temperature Surface 1 and apply it in the heating step. This may strike you as surprising because in the previous tutorial videos, we have generally created our boundary condition in the initial step. While in many of them, it would have been equally valid to create the boundary conditions during the load step, my personal preference is to define them in the initial step, since I like to think of them as existing even before the loads are applied. However, this is not possible in this procedure because Abaqus will not let you apply any non-zero boundary conditions in the initial step. In previous tutorial videos, our boundary conditions have involved fully or partially constraining the instances by setting either a few or all of U1, U2, U3, UR1, UR2, and UR3 equal to 0, depending on which degrees of freedom we wish to constrain. However, in this case, we wish to set the temperature boundary condition to a non-zero value, hence we cannot apply it in the initial step. If you try to select the initial step here, Abaqus will not allow you to specify a magnitude for the temperature when you click Continue, and will instead set the magnitude to 0 without any option to edit it. Set type for selected step to temperature. Abaqus prompts you to select the regions for the boundary condition. Set the distribution to uniform and the magnitude to 400 degrees Celsius. Similarly, create another boundary condition named constant temperature surface 2. Set this one to a temperature of 350 degrees Celsius. We can now create the heat flux load. Set the step to heating step and the type to surface heat flux. Abaqus prompts you to select the surface for the load. Select the surface in the viewport and then click Done. Since we are using SI units with length in meters and temperature in degrees Celsius, consistency requires that the heat flux is specified in watts per meter squared. We will give it a magnitude of 5000. We leave the distribution at uniform, which is the default. If instead you wanted to create an analytical field represented by an expression, you could choose user-defined and click Create. We also leave the amplitude set to the default of ramp, which, as mentioned before, will linearly increase the heat flux from 0 to 5000 watts per meter squared over the analysis step. Now we add convection and radiation to the model. Both convection and radiation are treated by Abaqus as interactions and must be defined in the interaction module. Convection can be defined in the interaction module by creating a surface film condition interaction or a concentrated film condition interaction. We will use the former. Abaqus prompts you to select a surface. This can be done in the viewport. In the Edit Interaction dialog box, leave the definition at the default of Embedded Coefficient. This allows one to specify the film coefficient in this dialog box. If the definition is set to Property Reference, the film coefficient can be defined as a function of temperature and field variables using a film condition interaction property. And if the definition is set to User-defined, non-uniform film coefficients can be defined using a user subroutine. Specify a convection coefficient or a film coefficient of 13 watts per meter squared per degree Celsius, which is consistent with SI units and the Celsius temperature scale. Leave the film coefficient amplitude set to the default of instantaneous. Set the ambient temperature or sink temperature on this surface to 200 degrees Celsius, and leave the sink amplitude set to the default of ramp. Radiation can be defined in the interaction module by creating a surface radiation interaction for distributed radiation or a concentrated radiation to ambient interaction for a node or node set. We will use the former. Abaqus prompts you to select a surface from the viewport. Look at the Edit Interaction dialog box. For the radiation type, the choices are to ambient and cavity approximation. To ambient indicates that heat transfer is to the surrounding environment. Cavity approximation, on the other hand, tells Abaqus to approximate cavity radiation in three-dimensional models using uniform emissivity, a closed cavity, and an average cavity temperature. Choose to ambient. The ambient temperature should be specified in degrees Celsius to stay consistent with SI units. Set it to 320 degrees Celsius. Basic heat transfer courses or experience in this area will tell you that the emissivity has no units and must lie between 0 and 1. Assume that our copper block has a thick oxide layer, which is known to have an emissivity of 0.78. An important thing to keep in mind when working with radiation in Abaqus is that the analyst is expected to specify the value of the Stefan-Boltzmann constant, as well as the value of absolute zero for the temperature scale being used. Right-click on the model name in the model tree and choose Edit Attributes. Since we are using SI units, we set the Stefan-Boltzmann constant to approximately 5.67 times 10 to the negative 8th joules per second per meter squared per degree Celsius to the 4th power. And since we are using the Celsius scale, we set absolute zero to minus 273.15 degrees Celsius. If you don't specify the Stefan-Boltzmann constant and the absolute zero for your temperature scale, Abaqus will not run an analysis which includes heat transfer by radiation, but will issue an error message. At this point, we've created constant temperature boundary conditions on two faces of the block and applied heat flux, convection, and radiation separately on three other surfaces. You're probably thinking we will now define the remaining surfaces as being insulated, but we have actually already done this. If you do not assign a temperature or any sort of heat flux load or interaction, Abaqus assumes that there is no heat flow through the surface. Therefore, these surfaces are perfectly insulated. This is referred to as a natural boundary condition and is useful if you desire a surface to be perfectly insulated or if you would like to apply a symmetry boundary condition. Let's proceed with meshing the part. Since we have a dependent part instance in the assembly, we mesh the part in the part module. When setting the element type, we select both partitions at the same time by drawing a rectangle around the entire part in the viewport. We set the element type to 8-node linear heat transfer bricks. We'll set the approximate global size to 0.25, a coarse mesh for an actual study, but sufficient for our demonstration purposes. We then create a job named Heat Transfer Job, give it a description, and run it. Abaqus informs us that history output has not been requested. We will tell it to continue with the job submission by clicking Yes. Let's view the results. By default, the plot state is undeformed, Hence you see the undeformed block with the mesh elements in green. We shall display the temperature at the nodes. Go to Field Outputs in the Results menu. Change the output variable to nodal temperature at nodes. Abaqus displays the Select Plot State dialog box. If our plot state had already been a contour, it would have been updated to show the nodal temperatures. However, since the current plot state is undeformed, Abaqus asks you whether you wish to leave the plot state as it is, or change it to a contour plot. Choose Contour and click OK. You see the nodal temperature distribution on the part. Another way of doing this in Abaqus is to use the variable list in the Field Output toolbar. Usually we orient the part using the Rotate View tool. Abaqus does, however, allow you to view a part at a direction perpendicular to one of the coordinate planes, such as top view or side view. This will allow us to see the results a little better. Enable the Views toolbar by going to the View menu, expanding out Toolbars, and choosing Views. The Views toolbar is displayed on the screen. We can use this to better view and understand our results. Click Apply Top View to view the block from the top. The upper half, with a constant surface temperature of 400 degrees Celsius and a heat flux of 5000 watts per meter squared, is colored red, indicating high temperatures, whereas the lower half is blue due to the lower constant wall temperature of 350 degrees Celsius and heat loss by convection and radiation from this region. The contours gradually pass from red to blue from end to end. However, you notice that the contour bands are not perfectly horizontal from left to right, but are curved. This is because we have heat loss by radiation from the left surface, hence the temperature drops faster on the left side than on the right as you move from top to bottom. Click Apply Right View to view the block from the right side. The area directly under the surface heat flux is the hottest. The contour lines on the right side of the plot indicate that it is hotter on the top surface than on the bottom surface as one moves from right to left in the region near the heat flux zone. However, once you reach the region with heat loss by convection, the contours bend the other way as the surface with convection cools faster than the opposite surface which is insulated. Aside from the default views, there are also user views marked 1, 2, 3, and 4. You can save any current orientation from the viewport by clicking the Save View tool. The Save View dialog box is displayed. You can choose which of the views you wish to replace with this new one. Let's store it in User 1. Change the scale and position options to Save Current. This will not cause the view to auto-fit to the screen, but will instead have the same zoom level as the current view that you are saving. Now if you zoom in and out in the viewport, you can return to the original view by clicking on 1. If you switch to another view like the bottom view or top view, you can once again return to this view by clicking 1. The Views toolbar, like any other toolbar in Abaqus, can hover in an undocked state over the viewport, or you can drag it into a dockable position by holding onto the blue ribbon at the top. You can also right-click on it and choose one of the docking options.